Our next topic is Archimedean property of a real number. Consider an example. Here we got the 6 balls at the right side and 1 ball at the left side. X equals to 1 is a natural number and y equals to 6 is natural number as well as a real number. Here is x is any number greater than 0 and y is any number belonging to the real numbers. Suppose now we add 1 extra ball to the left side. Now there are the 2 balls present at left side and 6 balls as it is present at right side. At right side more balls, therefore it is inclined towards right. Here we are having x equals to 2, y equals to 6, where x is greater than 0, of course x is equal to 2, that is greater than 0, and y is a real number. Now suppose we add 1 more ball at left side. Now we got the 3 balls at LHS and 6 balls as it is at RHS. Now adding 1 more ball at LHS. Now total balls at LHS are 4 and RHS as it is 6 balls. We do find that as the balls are added to the left side, the inclination at RHS is changing. Adding 1 more ball to the left side. Now total balls at LHS equals to 5 and total number of balls at RHS remaining same. Now by adding 1 more ball towards LHS, the total number of balls left side and right side are equal. By adding 1 more ball to the left side, we do observe that LHS has become greater than RHS. In this way, if we keep on adding 1 ball every time to the left side, the total number of ball at LHS will keep on increasing. In this way, if we keep on adding balls to the left side will keep on increasing and left side will remain larger than RHS. This experiment of balls will help us to understand Archimedean property of real number and well ordering property of natural numbers. Now let us define Archimedean property of real number. Archimedean property can be defined for a given order field. Given field has any 2 positive numbers x and y such that x is greater than 0 and y belongs to R. Then there is a compulsory number n is present which is greater than 0 and n is a natural number such that nx greater than y. In previous example, we had seen when 7 balls added to LHS, LHS become greater than RHS. In above experiment, in beginning we had 1 ball to the left side and 6 ball to the right side, but when the 7 ball added, the LHS became larger than RHS. At beginning x was 1 and y was 6, but when 1 multiplied by 7, it became greater than y. 7 into 1 greater than 6, n equals to 7, implies nx greater than y. 7x greater than 6 or 7 into 1 greater than 6. In general way, I can write 7x greater than y. This is nothing but outcome of Archimedean property of real numbers. Archimedean property of real number can be established, can be proved by inductive property of set of natural numbers or by using well ordering property of natural numbers. Archimedean property of R by using inductive property of n. For that I am considering a set of natural number 1, 2, 3, 4 and so on. Now consider any two numbers x comma y, where x is a natural number, y is any real number. Now consider two natural numbers n and n plus 1, and we already know that if x comma y are the two numbers given, then we can write nx greater than y. Now consider case number 1. For nx greater than y implies n is greater than y upon x, where y upon x is a real number. Therefore n greater than r. Now for n plus 1, if it is true for n by inductive method, it must be true for n plus 1 as well as. Therefore n plus 1 greater than y. Here also n plus 1 greater than y upon x. Y upon x is nothing but r, implies n plus 1 greater than r. From above both the cases, we do come to one conclusion, that n plus 1 Rn is always greater than r. This proves the validity of Archimedean principle. Consider two numbers 10 and 11. Now let us arrange these numbers in set S. S is a subset of natural numbers. In this set we observe 10 is smaller than 11, implies in this set there is one element smaller than other element. 10 is the least element of this subset of natural number. Now let us introduce one more number 2 to this set. Now in this set there are the three elements 10, 11 and 2, and we do observe that now earlier 10 was smaller, but now 2 is least element. In earlier set also a least element was there. In this set also the least element is 2. Now we bring another natural number 1 to this set. Now there are the 4 elements in the set and 1 is the smallest element. That implies even this set has least element, and the least element of this set is 1. Now consider some example of subset of natural numbers. In the example number 1, I have subset of natural number s equals to 2, 5, 9, 11 and 100. We do observe that 2 is the least element of this subset S. Similarly, if we have the another subset of natural number comprising of 100, 1000, 555 and 111, all are natural numbers, but the least element is 111. Even this subset is having a least element. In another example, I got another subset of natural number comprising of 12, 5, 202, 9998. Even though the elements are arranged in zigzag manner, even though we do observe that there is a one smaller element and the least element is 5. So irrespective of arrangement of subset of natural numbers, we do observe that every subset of natural number has a least element. They are having some serial order of increasing, that is they are arranged in the proper order, that is they are arranged in the well order. Therefore the arranging of natural number in well order manner, in a serial manner, is nothing but called well ordering property of natural numbers. Now let us define well ordering property of natural numbers. For that I have n equals to a set of natural numbers. If I start writing these natural numbers from 1, 2, 3, if I keep on writing, I can write up to infinity. Up to infinity, even though I write, there are the some numbers beyond infinity remain unwritten. Therefore set of natural number is unending. Out of that, let us consider a subset S. This subset S, let us say, consisting of A, B, C, D, E, F, where A, B, C, D, E, F are natural numbers. The subset of natural numbers S equals to A, B, C, D, E, F will consist of increasing order of numbers. That means there are the some number smaller than other numbers. These numbers can be arranged in increasing order. That implies the set S will have a least element, least number. Definition of well ordering property of natural numbers. If n is a set of natural numbers and S is a subset of natural numbers and S is not empty set, then every non-empty subset of n has a least element. Now we are going to prove the theorem. If x greater than 0, then every y belongs to R. There exists n belongs to n such that nx greater than y. To prove nx greater than y, we consider two cases, case 1 and case 2. In case 1, we are having y is smaller than or equal to 0, and case 2, y is greater than 0. In case of case number 1, y is smaller than 0 and y is real number, x is integer, a natural number. So, and n is any number belonging to natural number. X is greater than 0. In that case, if you select any number, for example n is equal to 2 and x is equal to 5 and y is smaller than 0, so I can select y equals to -1. So in that case 2 into 5 will automatically greater than -1. 10 is automatically greater than -1. That means when y is less than or equal to 0, nx greater than y automatically stand true. Now consider case number 2. We have to prove nx greater than y. That is a given theorem. But on the other hand, let us assume that given theorem is false. If the given theorem is false, in that case it get reversed, that is nx is smaller than or equal to y. If nx smaller than or equal to y, in that case y would be upper bound. If nx smaller than or equal to y, then by completeness property the set S must have some supremum in R. Let U be the supremum value of S. In that case nx will be smaller than or equal to U. If it is true for all natural number, and if the expression is true for n, it must be true for n plus 1, that is n plus 1 is the next higher number. By mathematical induction, n plus 1 into x smaller than equals to u. This is true for all natural numbers. And x, opening the bracket, taking x, subtracting x both sides, so we get u minus x. This is true for all n belongs to n. When nx is smaller than u, then u was the supremum value, and now nx is smaller than u minus x, then u minus x is another supremum value. How a given set can have the two supremum values? U minus x smaller than u, this is a contradiction to our assumption that u is a supremum value. Therefore nx smaller than y is wrong assumption. This is not valid. From above discussion for set S, which was the subset of natural number, and we had discussion that there is always x and y are present such that n is greater than y. That was the first discussion, and later on we had a contradictory statement, nx is smaller than or equal to y. Now out of the two statements, out of the two outcomes, nx greater than y proved to be correct. Why nx greater than y is correct? The reason is, from nx greater than y we come to the conclusion that given subset of natural number has only one upper bound, whereas nx smaller than y tells us that given subset of natural number has two upper bounds, and these two upper bounds are u and u minus x, and u minus x smaller than u. It contradicts that u is the supremum value of S. Therefore nx smaller than or equal to y is a wrong statement, and it proved to be wrong. Therefore nx greater than y is correct statement. From above discussion we come to the conclusion that Archimedean property of real numbers is correct, and the statement nx greater than y always exists, this is also correct. Hence, we establish ns greater than y.